Good evening to everyone. Am I audible? Hello. Am I audible?
Yes, sir.
PPT. Okay.
Yes, sir.
Okay. 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 So let's start with superconductivity. We already covered up the previous solid state physics part. That is imperfection of solid already in YouTube. If there is any problem, you must contact with me by on call or WhatsApp. Okay. Today we start the superconductivity. Okay. What do you mean by conductivity? Let's start. That conductor. Conductor means the material. The material who is sorry. What is conductor? Conductor. Conductor means the material who is can conduct the electrical current. Conduct the electrical electrical current by free electrons. Free electrons. Why free electrons? Free electrons. Right? Consider this is a conductor, and within this conductor the electron flow opposite to the current direction. If the current direction along that direction, the electron flow towards that direction. And the current or the resistance, if you want to say with in terms of resistance, you can say if we increase the temperature, this is this temperature and this is the resistance of this conductor, the resistance will be increased with the increasing temperature, right? Why? because of the because of the thermal agitation of the atoms as well as for electron. Thermal agitation, right? Thermal agitation means the atom molecules and atom. Some the okay, the atoms or molecules within the conductor is thermal agitated. They are thermally vibrated, and due to this vibration will be increased with the increasing temperature. If we increase the temperature, the vibration of these molecules or the electron will be increased. That's why the number of collision also increase. That's why the resistance increase. So due to thermal agitation, the collision increase, collision with the electron or electron molecules, electron or electron molecules or nucleus, you can say. Due to this collision, the resistivity increases, resistance will be increases. Actually, the resistance is nothing but rho L by A. L is the length and A is the cross section area of this conductor. So these two parameters can related to the shape of this conductor. This is connected or the related to the shape of this conductor, shape of this conductor, and this rho is depend on this material. This is the material property. Okay, so if you take two aluminum, then the rho will be the same. This there is the impurity will be the same, then the rho is the property of this material. So you can say this resistivity will be changes with the temperature as this. Okay, so if the temperature will increase, resistance will be increased, that means the resistivity will be increased. The if resistivity will be increased, there is a loss, energy loss. Resistivity increase, resistance increase means there is a energy loss. Okay, so there is a energy loss by heat energy, energy loss, mainly heat energy. There is a energy loss, right? So, to remove or minimize this energy loss, scientists are thought if we reduce the temperature, the resistance will be reduced, because with increasing temperature, if temperature increase, resistivity also increase, or resistance or resistivity you can say this is also increase. This resistivity increase mean the energy loss, energy loss, energy loss. Okay, so to reduce this energy loss we can reduce the temperature. So by reducing temperature, resistivity must be reduces, right? So experimentally they got some result. Suppose this is temperature axis and this is the resistivity axis. Okay, so if we reduce this temperature, the resistivity will be reduces. uh, resistivity will be increases like that. Okay, the negative temperature is not possible like that. Okay, but experimentally, 1911, suppose the experimentally 1911, 6th April, 6th April, uh, the scientist Heike Kamerling's Kamerling's Kamerling ohms, they study the effect of the lowering the temperature of the mercury. They study with mercury. This is the metal, conducting material, you know. They study with this mercury, and they he observed that at a certain temperature, and below certain temperature, the resistivity does not lower gradually. This nature will be gradually, but at certain temperature, in case of mercury, this will be 4.2 Kelvin. The abrupt change, their change will be abrupt. The nature will be like that. But after a certain temperature, the fall in resistivity is abrupt. This temperature is 4.2 Kelvin in case of mercury, right? So, in principle, by this nature, we expect the curve will be like that. With decreasing temperature, the resistivity will be decreases. But in case of mercury, he got the result that at temperature 4.2 Kelvin, the resistivity reduces sharply and the resistivity becomes tends to zero. That means the current will be increases huge, 10 to the power 6 order times increases from that point to that point, and this nature is sharply reduces. Okay, so after this below this temperature, this temperature is called the critical temperature. This temperature is called critical critical temperature. Temperature below this temperature, the resistivity becomes zero, or nearly zero, 0.0000 something. So this taken as the resistivity is zero and the current will be infinity, not infinity, this is very much higher compared to that point. If we taking current for that temperature and for that point, you can compare that this will be 10 to the 6 time or above. Okay, so we can consider this is a zero resistivity. That means the conductivity is maximum or superconductivity, because the conductivity is nothing but inverse of the resistivity. If resistivity will be zero, the conductivity will be maximum. That's why this is called the superconductivity. So this is called as superconductivity. Super superconductivity. And before that, this is a normal state, right? Normal state. So superconductivity is not a material. Material is Hg, right? Mercury is the material. Its state is superconductivity. Below that temperature, superconductivity is the state of this mercury, and above the Tc, the this is a normal state. Okay, so superconductivity is a state, not a material. Material is Hg. Hg is the material. Superconductivity is the state of this material. This is another state. Okay. So superconductivity is another state of the material, and the below this temperature, that is the critical temperature, below the critical temperature, this material shows this superconductivity nature, where the conductivity is very high. This conductivity is very high, and the resistivity is tends to 0. This is very high for the superconductor, or the superconductivity is the state, and the material at that temperature called the superconductor. Okay, very high. So you can say that in superconductivity, or in superconductivity state, superconductivity state, in the superconductivity state, the electrical current flow in superconductivity state, the electrical current flow, electrical current flow, electrical current flow in the electrical current flow within any loop continue, or without power loss, any loop forever, or continue without power loss, with without power loss. Is there any problem? Power loss, without power loss. Okay, so if this is a superconductor, that means the temperature in case of mercury, this is below the temperature below the Tc. This is becomes a superconductor. In this superconductor, fall, if you originate a current flow within that superconductor, this is a superconductor material. If you follow this current within the superconductor, they will be continue without any loss. They will be flow within the material without any loss. Oh, suppose this is a superconductor material, that means the temperature below T less than Tc. In this material, if you allow to flow a loop of current, this is a loop of current, this will be continue, without any power loss. This is the superconductor. This is the superconductor, or the state is known as superconductivity, in which the current flow within this material having no loss. Okay, due to the resistivity, the current will be no loss. This is the superconductivity. superconductor, or the state is known as superconductivity. Okay. So there is a important parameter, that is the temperature, right? Because in case of mercury, this temperature or Tc is 4.2 Kelvin. Temperature is very important parameter in case of discussion of the superconductivity. In case of ice, this temperature, the lower temperature, how we can find make the as much as lower temperature? The idea is, in case of ice, this temperature will be 273.15 Kelvin. Okay. In case of dry ice, if you say dry ice, what is will be the temperature? The temperature will be 194.65 194.65 Kelvin. In case of liquid nitrogen, in case of liquid nitrogen, 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 in if you are will be the research in any experimental lab, you will be aware about the liquid nitrogen. The temperature of the liquid nitrogen is the 77 Kelvin or 77.15 Kelvin, right? Liquid nitrogen temperature of liquid nitrogen is 77.15 Kelvin. In case of liquid helium, in case of liquid helium, this temperature will be 4.04 Kelvin. So you by using this liquid helium, we can get the this lower temperature that is the 4 point. In case of mercury, this is the 4.2 Kelvin. Okay, so by using the liquid helium, we can get this type of temperature. If we say another material, in case of mercury, this temperature is 4.2 Kelvin. The Tc, this is the Tc, and this is the superconducting material, right? In another example, lead, for lead, this temperature is 7.25 Kelvin. Actually, for using the superconductor, that means the low resistivity is the very useful for our daily life. But this such lower temperature production will be uh, will be not useful as a commercial, because to produce the low temperature we need electricity. So this is a drawback for this low temperature. So we need to find out at the higher temperature towards the room temperature, but room temperature is if not possible, we need to at least go to the liquid nitrogen temperature or the dry ice temperature. Okay, so if we produce the superconductor by metal or any alloy, and by metal or any alloy, sorry, by metal or any alloy, we our target is to target our target is to reach the superconductor with the our target is to uh, superconductor with the Tc, that is the no, critical temperature must be above that temperature, such that by using dry ice or the liquid nitrogen we can use the superconductor in our daily life uses. Another example is cobalt. For cobalt, this temperature is 18.5 Kelvin. For yttrium cuprous oxide 7, this temperature is 90 Kelvin, nearly 19 Kelvin, 90 Kelvin. In case of Tl2, Ca2, these are the alloy, these are the metal. Okay, by using alloy. Actually our target is to produce superconductor with the high temperature. This was 125 Kelvin. I want to give another example, that is the H2S. H2S, hydrogen sulfide, at very high pressure, at very high pressure, the TC, that is the critical temperature, above the below this temperature the material vs a superconductor, or the state called as the superconductivity. This temperature is 203 Kelvin. This is more useful, but these are all under the in the research field. Okay, so for application or the your daily life application, this will take more experimental result to increase the TC of this material by using metal or the alloy. This is our target to achieve, because for the application of this superconductor. Okay, so they discovered the superconductor first discovered by Kevin Lingons in 1911. The electrical resistivity of the many metals and the alloy drops suddenly to zero when the specimen is cooled sufficiently low temperature. This temperature is known as TC. Below the TC, this phenomena is called the superconductivity and or the state. This phenomena is called as this is the state of this material is the superconductivity, and the material is called superconductor in that temperature region. And another property of the superconductor is very important. If we uh, supply a current within the superconductor, then it will be runs years to years without any decay or any loss. The experimental done in 1963 by Mills and File that a ring of Hg and induce a current by applying magnetic field. This Hg at the 4 point or below the 4 point, the T of this temperature 4.2 Kelvin. So this becomes a superconducting state, right? If we apply the current within this state, the current half life is 10 to the power 5 years, 10 to the power 5 years. Can you imagine how long this current will be flow within this conductor? So there is no loss, effectively there is no loss of current in the superconducting state. So these two are the important experimental result which are the basic of the superconductor. First superconductor established or the observed 1911, and the basic property of the superconductor, that is the zero resistivity, that is in the infinite conductivity or the higher conductivity, that is proved by the experiment at 1963 by Mills and Files. Okay, and this is the image of the Cavenling's owns, where the experimental data point you can see this temperature is nearly 4.2 Kelvin. Above that, this resistivity or resistance is very high. Just below the 2.42, this resistivity becomes 10 to the power minus 5 ohms order. So this becomes tends to zero, nearly to zero. You can check the change from that point to that. There is the abrupt change. So this become a zero resistivity, right? So the resistivity of the mercury at low temperature, he was got Nobel Prize in 1930. At 4.2 Kelvin, the resistance drop of an unmeasurably small. The resistivity is small, very below with the unmeasurable. There may be a resistivity, but this resistivity is not measurable. Okay, this is a phase transition with the transition. So this state at called as the normal state. This state is called normal state. Okay, and this state is called the superconductivity state. Superconductivity state. Okay, these two are the state of this material. Here the material is Hg. This example is for Hg mercury or right? Next one is the, this is the experimental result for the, actually this curve is measured like that, 4.15 Kelvin taken as the 4.2 Kelvin. In this experiment, we saw that there is a jump of the resistivity 4.2 will a certain mercury at this low superconducting state. This is the state. Okay. In general, for a metal, the resistivity decrease with the decrease of the temperature. Generally, the resistivity decrease with the decreasing the temperature. This is the natural phenomena with this relation. The resistivity will be increasing with temperature increases, and if you say this is decreasing, if T will be decreasing, the resistivity will be also decreasing. Here the rho zero is the for impurity. This is the non-magnetic phenomena. This is the due to impurity, and this is for the phonon scattering. This temperature effect due to phonon scattering, the resistivity of this material actually depend on two main factor, that is due to impurity and the phonon scattering. The impurity part is constant with respect to temperature, and phonon scattering will be increasing with the phonon scattering part will be increasing with the temperature. You can see this is the temperature axis and the resistivity axis. There can be three type of nature. This is the normal, and this can be a impurity material, and this is for different pure like material. This nature will be available. Okay. And if you see, there is two graph for gold with impurity 0.015, the upper one, and for lower one is the impurity is the 0.005%. With increasing the impurity, the resistivity will be increases, right? This is the fact for the metal. You know, for semiconductor, with applying impurity, that is the doping, and for that the resistivity will be reduces. But in case of metal, if we doped in this metal or the impurity, the resistance will be increases. And this phenomena draw up in this graph. You can see the timeline of the superconductivity, how at first the 1908 this Kelvin ohms achieve very low temperature producing liquid helium. Actually, they wants to lowering the temperature, but how? At that moment there was a 77 Kelvin, that is the liquid nitrogen was available, but liquid helium is not available at that moment, 1908. Okay, so at that time they produce, or Cameling's owns produce the liquid helium whose temperature can be below 4.2. You know, this is the 4.04 Kelvin liquid helium. At 1911, Collins owns and host observed the sudden drop of resistivity. Okay, this is the superconducting British era will be start from 1911. From 1914, persist current experiment owns was observed. Mesner was observed 1933 and 35, 50. BCS theory 57, 62. Josephson effect. We will study that this BCS theory, Josephson's effect will be studied in this um, semester. Okay, and lastly, this was 39 Kelvin. The two tissue of that, it took 70 years to get fast accelerator from the conventional superconductor. Okay, so our target is to produce the superconductor with the higher temperature, that is takes 70 years for the first produce 2003 like material. And you already know the material already under research purpose, the 125 Kelvin or 203 Kelvin is the high very high pressure. This will be at the very high pressure. Okay, so this research are already ongoing research to produce the superconductor at the higher temperature for using the our daily life uses. And this is the list of superconductor, you can see the blue color are the superconductor with at the ambient pressure. The pressure, the normal ambient pressure, by normal ambient pressure, the superconductivity was observed in the material which are in the blue color. In case of the green color, only under the high pressure will be observed, and the carbon is the yellow color due to the two type nature will be observed, because there are the uh, isomer, various type of isomer for carbon, fluorine, graphite, granite. Due to this different formation, this carbon can be used as the high pressure. They uh, some isomer can behavior as the superconductivity with high pressure, and some isomer behavior with the superconductivity at the ambient pressure. That's why it's a different color with the carbon, and the blue are at the normal pressure, ambient pressure. You can see the age is the blue, and the others one there is a green color which is will be the high pressure H2 S, the H2S. You can see the sulfur is in the high pressure region. That's why we already says that H2S will the superconductor at the higher, at the high pressure, right? So from the periodic table you can also confirm that information. Okay, so this phenomena, a large number of element alloy and the compound at the zero resistivity below the temperature, that is the critical temperature, is the superconducting transition or the critical temperature. This temperature is known as the critical temperature or the superconducting transition. The critical temperature is that at which the transition from the normal metallic state to superconducting state. Okay, so this is the superconducting state. The temperature below which the state is superconducting, and above which this is the normal. This is called as the critical temperature or the superconducting transition temperature. Clear? Occurrence. These are the there are large number of superconducting. This is a hot topic in the research field to produce the superconductor with the higher temperature. And you can see this example already done. You can see here also. Okay, how the superconductivity can be vanishes. I want to say we need to rejoin in this session, so I just use here the superconductivity can be vanishes using different types. Before that I want to write down some. Okay, that's no problem. The superconductivity can be vanished or can be destroyed by three processes. First, number one, thermal thermal effect. Thermal effect, that is the, if we increase the temperature, that is the high temperature above the Tc, high temperature above the Tc, that is the T greater than Tc, then the superconductor transfer from superconductor transfer from superconductor to normal state. Okay, at the temperature above the Tc. Next, using magnetic field. Using magnetic field. Just use the magnetic field. You can destroy the superconductivity states of this material, right? And third one is the high current flow. Superconductivity low resistivity or zero resistivity tends to zero, not actual zero, tends to zero resistivity. So you can say the current will be the infinity, but that is not happening. The resistivity tends to zero, which cannot measurable in the instrument. Okay, so the current, if we apply huge current in the superconductor, then the superconductivity phenomena also destroy. So high current density. High current density. Okay, these three are the effect by which we can transfer the superconductor to the normal state of this metal or the alloy. Okay, so we need to, if you know the thermal effect, this thermal effect, just increasing the temperature, the thermal agitation of this nuclei also increases. That's why the superconducting state is the lowering. Superconducting state is the thermal at the lower temperature. What happens at the lower temperature? Thermal agitation of this will be reduces, right? So the thermal agitation reduces, and the electron will be ordered. The electron can move in this material, or the conductor will be ordered, right? So at the high temperature the orderness will be destroyed. That's why the superconducting material will be destroyed. In the next video, just want to rejoin, we want to discuss the magnetic field, and the next class, in the next class we will be discuss effect of the high current density, effect of the superconductor, how the superconductivity can be destroyed within the superconducting material. So please rejoin in this class again.